Welcome to the Deep Dive, where we take your source materials, bypass the noise, and really deliver the exact insights you need.
That's the goal.
Today, we are strapping in for a very, very specialized trip. We're going into the world of industrial infrastructure.
Yeah, this is a good one. We're dissecting the unsung heroes of manufacturing.
Absolutely. We're talking about the machine guards, the protective shields, all those engineered covers that ensure millions of pieces of industrial equipment run safely.
Every second of every day.
The sources we've received are, they're highly technical. They're focused entirely on something called power transmission guards.
And these aren't your, generic safety signs or a bit of yellow tape.
No, not at all. These are heavy-duty component-specific covers. They're designed for, frankly, extreme environments. So our mission today is to synthesize this stack of details, explain precisely what these shields protect, and, maybe more importantly, illuminate the highly specialized engineering that makes them so indispensable.
Exactly. This deep dive is really about the structural integrity of safety itself. If you want to be truly well-informed about the industrial world, you have to look past the huge machines.
Right.
You have to focus on the small, critical pieces that manage risk. We are extracting the essential knowledge on how to mitigate exposure to what the sources define as rotating hazards.
Okay, rotating hazards.
And understanding why a generic cage just won't cut it when you're dealing with high-speed power transmission.
Okay, so let's unpack that. We're talking about components that are designed to transfer just massive amounts of kinetic energy.
Right. Belts, chains, gears.
All moving incredibly fast. So what is the core, the fundamental problem that these specialized guards are trying to solve?
Well, the fundamental goal, and the source material is very clear on this, is the absolute protection of personnel and equipment from any exposure to that movement.
So it's a barrier.
It's a barrier, yes. The primary danger, of course, is the general rotating hazard. Anything spinning fast enough to cause an injury. But, true industrial risk analysis goes so much deeper than just it's spinning.
I see. So it's not just a general danger.
No. The focus shifts to where that energy transfer is at its most dangerous. And that's why the sources drill down on two very specific high-risk scenarios.
And what are those?
Pinch points and entanglement.
Okay, define those for us.
A pinch point is where two components move together and create a shear or a crushing hazard. So think about a belt meeting a pulley.
Got it. Yeah, I can picture that.
An entanglement is the risk of catching loose clothing or hair or even a limb on a rotating shaft or chain, which then draws the worker into the machine.
And these are not minor hazards we're talking about.
Oh, no. They represent the most severe, often catastrophic injuries you see in industrial settings.
That distinction you made, between a generic rotating danger and the specific risk of entanglement or a pinch point, that feels critical.
It is.
And I find the operational paradox here just fascinating. The primary job of these solutions is protection, obviously. But if the safety engineers just decide to, weld heavy steel boxes around everything, they've created a whole new problem.
They absolutely have, and that is the central engineering challenge. How do you provide comprehensive absolute protection against entanglement and pinch points while at the same time
You have to let people do their job.
you have to ensure equipment access for maintenance, for routine inspection? If a guard is too difficult to remove, or if, say, accessing a lubrication point requires a 2-hour system shutdown and a full teardown,
People are going to find a way around it.
that guard becomes a liability to productivity, and it will get bypassed.
So the trade-off is often safety versus the speed of maintenance. If a guard guarantees downtime every single time a technician needs to check a fluid level, it just defeats its own purpose.
Exactly. A safe design has to be a usable design. The source material really emphasizes this by specifying that many of these solutions have to be modular or easily removable.
Because if you fail to design for maintenance,
The risk mitigation is only temporary. Workers will prioritize uptime, and they'll inadvertently increase their hazard exposure. And you also have to think about the durability of the guard itself. A flimsy guard that gets damaged by a tool or some debris is also a failed safety measure.
that makes perfect sense. So if the goal is to protect against these pinch points and entanglement while still maintaining access, what are the biggest categories of equipment that need this kind of specialized protection?
Based on the source list, we can categorize the general equipment that forms like the backbone of power transfer.
Okay.
First, you have the support structures, so the end shaft bearings and pillow blocks, which actually anchor the rotation.
The foundation.
The foundation. Second, the actual power delivery units themselves. We're talking industrial transfer pumps and motors.
The engines of the whole operation.
Pretty much. And then third, you have the ubiquitous systems that move that power across distances.
The belt and chain drive systems.
Ex-
And I noticed the sources specifically call out one major sector for extra detail. Conveyors. That
Yep.
tells me these long linear systems have their own unique and complex needs.
They really do. A conveyor is a dynamic system. It presents hazards continuously along its entire path, not just at the motor.
Ah, I see.
So the sources list dedicated guards for very specific conveyor components. Things like idler rollers, the drive belts themselves, the couplers that join different motor units or sections, and crucially, take up bearing covers.
So you're protecting components that are designed to move and shift under a load.
That's the challenge.
This is where we shift into the deep dive territory. Let's focus on the 5 specific guarding solutions that are detailed in the material, because this is the knowledge I think our listeners really need to absorb.
Let's do it.
So, starting with the foundation, and shaft bearing and pillow block covers. How does a cover engineered for a static bearing like that differ from just a generic cage?
Okay, so what's fascinating here is that it has a twofold role. These are heavy-duty molded covers designed to protect the exposed shaft ends and the pillow block bearings that house the rotating shaft.
Yeah.
The engineering specificity really comes down to materials and fit. First, they eliminate the immediate entanglement risk from the sharp, exposed end of the shaft.
Which can act like a spool, right? Just grab onto
A very dangerous spool, yes. But second, these covers are also engineered to provide environmental protection.
Ah, so protecting the machine itself.
Exactly. Pillow block bearings, they rely on lubrication and very precise tolerances. If debris or dust or moisture gets into that bearing,
Which is common in most industrial environments.
guaranteed, the life of that component is drastically shortened. So these covers don't just protect personnel from the machine, they protect the machine from the environment.
And that ensures operational longevity and prevents unplanned, very costly downtime.
It's a protection layer for both man and machine.
Which leads us directly to the next specialized item. Take-up bearing covers. Now this component, it sounds like it has a very different mechanical job.
It does.
So what exactly is a take-up bearing, and why does its sort of sliding nature need a unique guard design?
Well, if we connect this to the bigger picture, a take-up bearing is what's used to maintain the proper tension in a really long chain or belt system. You see them all the time in conveyors.
Okay, so it adjusts for slack.
Exactly. It allows the bearing and the shaft it supports to slide back and forth, adjusting for any slack or stretch in the belt. And because this mechanism slides, the length of the exposed shaft is changing dynamically.
So the distance between the fixed machine frame and the rotating part is always in flux.
Right.
That sounds like an entanglement nightmare.
It is. A standard fixed guard would either be too tight when the bearing is fully extended, which would cause rubbing and wear, or it would be too loose when the bearing is retracted, leaving a really dangerous gap. So the take-up bearing covers are these durable, molded solutions designed specifically to accommodate that sliding movement and the moving shafts.
So it's like a sleeve that can expand and contract.
In a way, yes. Its specialized shape ensures that no matter where the tension adjustment is, and maintenance crews might be checking that frequently, the point of contact and the entanglement risk remain fully shielded. It's a really elegant solution to a moving problem.
That is a powerful example of necessity driving specialization. Okay, let's move away from the mechanical supports and on to the actual power units, industrial transfer pump and motor guard covers.
Mm-hmm.
Now, we're often talking about fluids, chemicals, harsh environments. What dictates the design and the material choice here?
The material requirement is absolutely key. The source specifies these covers have to be highly durable and critically corrosion resistant.
Okay, so that's the big one.
It's huge. I mean, think about where a transfer pump operates. It could be near cooling towers, chemical baths, material processing lines where spills and constant moisture are we're guaranteed.
Right. A standard painted steel guard would just rust away in weeks.
It would rust and degrade rapidly. And it's not just that a corroded guard looks bad. A failed guard provides zero protection, and even worse, the failing material itself, like flakes of rust, can contaminate the process or the machinery.
That's a great point.
So these specialized covers, they're often molded from chemical-resistant polymers or special alloys. They ensure that the physical barrier stays intact. It protects the motor-sensitive electronics and shaft couplings from ingress.
And it maintains the shield.
For years, even under the most caustic conditions. This is where safety intersects directly with process integrity.
So you're not just guarding against a splash, you're guarding against this ambient chemical attack that would literally dissolve the protection over time.
That's the perfect way to put it.
Okay, now let's look at the heart of the power transfer. The belt and chain drive guards and shields. These systems can be vast, complex, and they require frequent intervention.
And this brings us right back to that maintenance paradox we talked about, and the solution detailed here is modularity.
Modularity.
Yes. These guards protect the most active components, the sprockets, the pulleys, the transmission housing. And if we connect this to the bigger picture, these are the components that need regular lubrication, tension checks, and eventual replacement.
And the downtime here is incredibly expensive.
Massively expensive. So the modular guarding solutions specified in the sources, they allow maintenance personnel to quickly and safely remove a single section.
Just one piece.
Just one piece, often held by specialized secured fasteners to access one part of the drivetrain. And they can do it without having to shut down or dismantle the entire machine structure.
So that's the real nugget here.
It is. Modularity isn't just a convenience, it's a safety measure. It prevents workers from cutting corners by making routine access secure and straightforward. They come apart like high-tech Lego bricks designed for disassembly, but they're rock solid when they're locked together.
So the engineering is actually designed to incentivize compliance.
Yeah.
You make it easy for people to follow the safety protocol.
You make the safe way the easy way.
I love that. Okay, finally, let's wrap up with the specialized barriers for the conveyor path. The conveyor guards for idler rollers, drive belts, and couplers. These seem to protect the points where materials are moving over stationary parts.
Precisely. This final category is all about linear motion systems, and it is intensely focused on mitigating the nip points.
Nip points, another key term.
A very key term. A nip point occurs anywhere a belt or a chain is drawn into a roller, a pulley, or a sprocket.
Ah, so it's that entry point.
Yes, and these are exceptionally dangerous shear points. The force there is tremendous, and they present a very high risk of entanglement.
I can see that.
So these specialized guards, they secure the idler rollers, which often guide the return path of the belt. They shield the drive belts, and they cover the couplers that connect different conveyor segments.
And because they're integrated right into the operational path of the conveyor.
They absolutely must not impede the flow of materials being conveyed. They provide very, very tight clearances to prevent access to the moving parts, but without interfering with the product or the belt itself. It's a very difficult balancing act to achieve a fully enclosed danger zone while maintaining that continuous operational capacity.
That is truly refined engineering. The takeaway, I think, from these 5 distinct solutions is really powerful. The specialized nature of industrial safety means protection is not a simple bolt-on solution.
Not one size fits all.
No, it requires component-specific engineering designed to mitigate unique localized hazards, whether that's chemical corrosion or dynamic movement, or just the specific geometry of a shaft end.
Absolutely. What this source material really reveals is that true safety relies on engineered solutions that specifically mitigate entanglement and pinch points. They use covers that are durable, often corrosion resistant, and, crucially, provide secure yet necessary access for maintenance staff.
Right.
These shields, they're not just pieces of plastic or metal, they are meticulously designed interfaces between human risk and mechanical power. They are, the unheralded reason why industrial operations globally continue to function smoothly.
It certainly makes you look at a factory floor differently. You start appreciating all this unseen infrastructure. And considering how much engineering goes into designing a highly specific, modular, corrosion-resistant guard cover for something as basic as a transfer pump. Here's a final provocative thought for you to carry with you.
Yeah.
Think about all the enormous multi-million-dollar pieces of infrastructure out there, from deep-sea drill rigs to power plants. What are the specific, highly specialized, and often completely unseen safety systems that keep those operations running smoothly? We've really only scratched the surface of what it takes to protect the spin and, more importantly, the people who work around it.
Something to ponder next time you see a machine operating flawlessly.
That's all the time we have for this deep dive. We'll see you next time.